Ladies and gents, welcome to lesson 14, parts of a circuit. We will learn about the different types of circuits and their properties. Now we remember from the last few lessons we've been talking about three parts of a circuit. The voltage, which is the push that moves the electrons around a circuit. That push is caused by the fact that negative wants to move to positive. That's why the push exists. What is it pushing? It's pushing electrons. The more electrons it pushes, the more the current is. The current is the flow. If it's pushing a lot of electrons, then we have a high amount of flow. If it's pushing not very many electrons, we have a low flow. The higher the voltage, the higher the current. Of course, this current can't just flow easily like, it can't just flow easily like water out of a tap, because sometimes there are things that get in the way. Those things that get in the way, they are resistance, and they are opposition to flow. And they will want to push against the flow. So the resistance will push against the flow, and that's sort of how that works. But what I want you guys to remember is that resistance isn't a bad thing. It's sometimes a good thing. Remember, if we've got a light bulb, then that light bulb is part of the resistance. And we want that thing to resist because we want to use that energy. So these are the major parts. What we're going to talk about now, though, is a circuit. We said that if a battery's job is to move all the negatives to one side and all the positives to the other side, it's the circuit's job to balance out the charge. So really quickly, we're going to talk about what do we refer to as the parts of a circuit and what can they do. We're not going to talk about all of the beautiful parts to a circuit today. We're just going to talk about some of the basic ones. So let's start with talking about a circuit diagram and the symbols that we use in a circuit. So what scientists usually do, so this is an example of a circuit. This is how we would set up a circuit. We've got one wire here, one wire here, one wire here. We've got a switch. We've got a light bulb, which is providing a load or resistance, and we've got a battery here or a power source. Now, this is an actual drawing of what a circuit would look like. And if you were building a circuit in a lab, that's what it might turn out. But when we want to actually talk about this circuit with regards to maths, or when we want to talk about these types of circuits with regards to engineering, we need to actually find an easier, better way to draw these circuits. And so what we end up with is a circuit diagram. The circuit diagram looks like this. On the right, we have a circuit diagram. Some parts that I want to show you guys that are important here is, number one, wires are straight lines. We don't do curvy lines, we just do straight lines. Now, I fully know, of course, that if you were trying to attach a wire from here to here, it's not going to be a straight line. It's going to be all curvy and wavy. But for simplicity's sake, we use straight lines. What we also use is we use symbols. So they're the two parts that are important. The symbols that we use are important for us to understand what's going on. So these three symbols, this symbol at the top is the symbol for a battery. This symbol at the bottom is a symbol for a light bulb. And this over on the other side is a symbol for a switch. So if we look at the switch one, it actually makes sense. You've got a line here that is broken, and it can be connected, closed or open. The bulb sort of looks like a bulb because it's a circle. And yeah, the main types of symbols that I want you guys to learn are on the bottom here. From left to right, we have a cell or a battery. Technically, and this is a technical thing, technically a battery is more than one cell put together, but I don't care if, because it's just a beginner's sort of year 10 class, I don't care if you guys just want to know the basics. Angus, you good? Or you got a question?
Sorry, so I was just trying it out.
That's okay. That's no stress. The lamp is, of course, the light bulb. We've got a switch, we've got wires, and we've got a resistor. Now, a resistor is just a resistor. It doesn't actually use any of the energy. The energy gets lost in a resistor in the form of heat. I will point out that sometimes you may see resistors drawn like this. And sometimes you might see lamps drawn like this. That's because this is the US version and this is the UK version. I'm pretty sure. It doesn't really matter what symbol you used as long as you can tell. And the advantage, the reason that I like this symbol here for a resistor, and that's the one that I'm going to teach you guys, is because it sort of makes sense. In order for the electrons to go through this, they have to go up, down, up, down, up, down. They're going to lose energy. And whereas I sort of like this symbol for the lamp because it sort of looks like a light bulb. But yeah, these are the symbols that I want you guys to learn, and you guys will get some experience because we'll see these symbols a lot. I want to talk about, though, specifically the cell or the battery. And we'll spend a little bit of time talking about that. Now, the cell or the battery has two sides, okay? It has, a positive side and a negative side because a battery always has a positive and negative. Now, this is going to be a bit of a challenge for you guys. You need to find a way to work out which side is positive and which side is negative. How I remember which side is positive and negative is by using this. I like to imagine that this long side on the left, it's long and thin. So if I took this long and thin side, I could actually snap it in half. And if I snap this long and thin line in half, I could then take the two halves and make a plus sign out of them. So that means that the long thin side is the positive side of the battery. Now, in comparison, if I took this, thick small part here and I tried to snap it, I wouldn't be able to snap it. Okay, I can't break it up into smaller pieces. So because I can't break it up into smaller pieces, it has to stay like a negative. So that means this side is the negative side of the battery. That's how I remember it. You might want to make a, different thing. Maybe you could be like, I want to be tall and thin because then I'll be positive and happy, rather than being small and fat, which is a negative bad thing. You might want to have a different memory technique. You could probably have a weird memory technique got to do with, it's bad to be small and thick or something like that. I don't know. I'm not going to go into details here. But yeah, any way you can come up with to remember that the long thin side is the positive side and the small thick side is the negative side. When you've got a battery and you have more than one of these together, it would look like this. So here's one cell. Here's another cell. So this is a battery because there's more than one cell joined together, but it still has a positive side and a negative side. And that's going to be useful to us, especially because if we now want to draw, well, which way is the current going in this circuit? We know that it's coming out of the positive and going into the negative, because again, conventional current. And that's why we need to know which side of the battery is positive and which side is negative, so we know which way the current is going in the circuit. So that's batteries, that's the cell. I will quickly talk about, when we talk about, we'll talk about next is, okay, I want to talk about something called voltage drops. Now, this is sort of a new topic, a new idea. In a circuit, the electrons leave the battery with the maximum amount of energy or voltage, right? When they leave the battery, they have as the most amount of energy they will have for the whole circuit. So if I've got, let's say, call this one a 12-volt battery. This is a 12-volt battery. When these electrons leave, they leave with 12 volts. Now, as the electrons move around the circuit, they will lose their energy at different points of resistance, like a light bulb. And this is called a voltage drop. So I'm going to follow the path of the current, not the path of the electrons, the path of the current. As it goes around, it's got 12 volts here. It's got 12 volts here. When it gets to this circuit, it's going to go from 12 volts down to 0 volts. It's going to lose its energy. It's going to drop its energy at the light bulb. It's going to drop 12 volts. Okay? And then, of course, when it comes back up to the battery, it's going to come up with 0 volts, the lowest. At the end of the circuit, the electrons have 0 energy or 0 volts. So that's going to be the point where it's got the lowest amount of energy. Okay? So when we talk about, like, in the next lesson on Thursday, we're going to talk about, you know, if you have more than one light bulb in a circuit, you might lose 3 volts here and then 3 volts here. It might even be uneven. It might be you might lose 3 volts here and 7 volts here. So you can then say, well, how many volts?
If uneven, but if it's uneven, so does that mean they're like different type of batteries or they're the same?
What it means is that they're different types of resistance. Okay, we're going to talk about this in more detail next time. But great question. So if I've got a 3 volt, if it's losing 3 volts here, then that's like, okay, I've given my electrons a little bit of a hurdle. If I'm losing 7 volts here, then I'm giving them a big hurdle to go over. It takes a lot of energy to get over the wall compared to the amount of energy it takes to get over this little hump.
Yeah.
So that's what a voltage. So let's just talk about this. A voltage drop. The voltage drops are places where energy is lost, or we could say transformed. So you could have a motor instead, and that's going to have a voltage drop because it's going to lose the electrons are going to lose energy, but it's going to turn into like a moving motor or something like that. The last little bit that I want to talk to you guys about today is specifically about voltage drops. Is there is a resistance in the wire. Okay, there is a resistance in the wire because it's difficult for the charge to go down the wire. But what we're going to do in order to make our lives a lot easier is we're going to assume that the wires have 0 resistance. We're going to assume that if I have a wire and if I have 12 volts here and I go through that wire, I've got 12 volts here. And that's pretty accurate. Like, you don't lose much energy going through a copper wire. But it's just the point of this is trying to say is we just want to make our lives simple. We don't want to try and overcomplicate things. And then we also want to do this is, and this is something similar to sort of, I think, what Reese may have mentioned last lesson, the amount of voltage dropped at each component is calculated using Ohm's law. So V equals IR. So if I've got a current of, if I equals 1 amp and the resistance is 3 ohms, then that means 1 times 3, I'm going to lose 3 volts. If the current was more, then we would do that. And that's the basics of that. So first things first, that's it for this lesson. I want to quickly talk about what I talked about. First, I talked about the components. I said we draw things using straight lines, and we also use symbols. Some of the main symbols we're going to use are the battery symbol, the light symbol, the switch symbol, and the resistors. And then briefly I mentioned the positive part of a battery is the long thin side. The negative part of a battery is the small fat side. Voltage drops are places where electrons lose their energy, like in a light bulb, like in a motor, like in a speaker, and they drop voltage or lose energy. They lose enough energy so that when they get back to the battery, they have no voltage left. Last thing I talked about is resistance the wires have 0 resistance, and the amount of voltage dropped at each component is calculated using Ohm's law. What I wanted to finish up with the last little bit, I wanted to talk to you guys about these parts here. So this is the first page in Electronics 1. Okay. Now you guys can download this. You guys can print it off and fill it out. You guys can just copy the questions down. You guys could even just go 1A, 2A, I don't care. But I want to show you guys, this is the first page and this is what the second page looks like. I want to tackle 2 questions just so that you guys feel a little bit more confident. I'm thinking about doing question 3A. Is there anyone that wants me to do something different? We're good with 3A. So I'm going to do 3A. If you need some help with this though, and if you make your way through it and you get a particular question, you're like, I don't know how to do this at all, let me know. So let's look at 3A. If there is a current of 10 amps in a circuit for 10 minutes, what quantity of electric charge flows through the circuit? Okay, this is a question that's asking us about charge. It's asking us to find out what Q is. We have I. It told us I was 10 amps. And we have the time. The time is given to us as 10 minutes. But we can't use 10 minutes because we can't use minutes. We have to use seconds. So 10 times 60, because the 60 is going to be 600 seconds. Okay? So if I want to know I equals Q over T, I want to know the amount of charge. So that means I'm going to use the formula Q equals I times T. You don't know how I did that? Just over here, all the way at the top. I equals Q over T. Multiply both sides by T. Just going to cancel that out. I, T equals Q. So that means if I substitute I, which is in this case, where is it? I, which is 10 amps times t, which is 600 seconds, I get 6,000, and the units for this, the charge, are coulombs. I get 6,000 coulombs worth of charge. That's the answer to that first one. Are there any questions on how I did that? Does that make sense to people? I need to see at least one yes, or hear at least one yes before I move on. Yeah, cool. Thanks, John. Beautiful. Let's move on then. So that's how you would do that. The other questions are very similar. This guy down the bottom, though, this one down the bottom is a bit more challenging. Have a look at that. 7.2 times 10 to 26 electrons is discharged from a Van de Graaff generator in 0.1 seconds. What amount of current is flowed in this time? Oy, that one's going to be a bit hard. I'll give you a hint though. We know that one electron is 1.6 times 10 to the negative 19 coulombs. So if I have 7.2 times 10 to the 26 electrons, 1.6 times 10 to the negative 19, that will tell me the charge, that will tell me the released charge. So that's what you want to calculate here. Once you know the released charge and you know the time it takes to release that charge, you can work out the current. But I'm not going to work that out for you. I'm going to let you guys figure that out on your own. But that's some pretty good hints here. The second page has Ohm's law questions. Let's pick one. Okay, first person in chat to pick a question out of 1, 2, 3, 4, or 5. I'll do that one. I'll let you guys. Who picked first? That was Emre, who chose question 3. Beautiful, done, easy. Question 3. A battery replies, good question, Emre. You chose one which requires rearranging. A battery supplies 24 volts to a circuit and has a resistance of 12 ohms. What is the current? Okay, V equals 24. R equals 12. I is unknown. Well, let's use our formula. V equals IR. Well, I don't want to know V. I want to know what I is. So I'm going to divide both sides by R, which gives me V divided by R equals I. What that means is the current is going to be the voltage, which is 24 volts, divided by the resistance, which is 12. 24 divided by 12 is 2. The answer is 2 amps. So some of these you'll have to rearrange. Some of these you won't. If you aren't confident with how to and there's an example up the top here. If you're not confident with how to rearrange though, you can just use this formula here. V equals IR. I equals V over R. And R equals V over I. They're the only formulas you'll need. That should be enough information to get you through all of Electronics 1. Now, with the rest of this period, there's about what is it, about 20 minutes left in this period, maybe 15. Give some of them a try, even if you just start them.